Good morning, student. This is your physics teacher, and welcome to my online physics class. Today, we will study a very important law related to the viscosity chapter, and that law is Stokes law. You must be watching over here. Stokes law. Okay. So, what does Stokes law say? That whenever a metallic ball is moving through a liquid or fluid, whatever it would be, then there will be a force acting on it to decelerate the motion of the ball. Okay, then that force is written as 6 pi eta r v, where r is the radius of the ball and the v is the velocity called terminal velocity. Now I must be wondering that a new term has come over here, terminal velocity. For the time being, just remember that there is a velocity, terminal velocity. So the force is given by 6 pi eta rv. Don't ask me that how this relation has come. You can prove this relation through the dimensional uh, analysis way, okay, and some other way also you can prove it that the relation is true, and that way you can do. But for our syllabus point of view, I will say that uh, the derivation of this formula is not coming under the our syllabus, so we are not going to cover it. Just we should know that this is the Stokes law. The force is given by 6 pi eta rv, where r is the radius of the ball and the v is the terminal velocity. Now terminal velocity, let's start about the terminal velocity. Here I'm giving you one graph over here, showing you one graph. So from the graph you must be wondering that the graph, first of all, it rises up and thereafter it becomes parallel to the time axis. Now velocity is plotted along the y-axis, time is plotted always along the x-axis. So with the time, the terminal velocity increases, but soon after some time the terminal velocity acquires a saturation value. Now not terminal velocity, it is velocity. Okay, so the constant velocity with which it is now moving, and it is no longer increasing, that is known as terminal velocity. Okay, remember this thing, that is known as terminal velocity. So earlier, when it starts moving down the uh, an ideal liquid, not ideal, yeah, you can say ideal liquid. So in that case, there will be some viscous force, and as the weight is more, so it is moving with some acceleration, and the velocity, that's why it is increasing. But soon, uh, with the increase in velocity, okay, the viscous force also increases, and a time will come that velocity becomes constant. That constant velocity is known as terminal velocity. So if the question is asked that why, what is the statement of it, just remember this thing, that when a body falls from rest in viscous liquid of infinite depth, its velocity increases rapidly till it reaches a constant velocity called terminal velocity. So the graph part has been covered over here. Now we will go for the derivation of this terminal velocity. What is the actual expression, what is the mathematical expression? So here you are watching over here that there is a container, and we have to assume that the container is of infinite depth. Okay, so a ball, it's somewhat heavier, it is moving downward. So what are the forces that are acting on this ball? The first one is the mg weight. This weight is acting downward, always weight is acting downward, because weight is the force with which the body is attracted towards the center of the earth. And of course there will be some upthrust. Upthrust, you know, I think upthrust is also known as buoyancy force. Buoyancy force, okay. Buoyancy force or upthrust is actually equal to the weight of the liquid displaced. So earlier there was some liquid over there, and to get inside of the liquid, the metal has displaced some amount of liquid. The weight of the displaced liquid is actually acting in the upward direction, and that is known as buoyancy force or upthrust. So here we are assuming that the weight of the liquid is rho, and also sorry weight density of the liquid is rho, and also assuming that the density of the solid is sigma. Here we are going to the next part. So the upthrust over here, it will be V rho g. What is V? V is the volume of the liquid, volume of the ball, because uh, the volume is, let us suppose, V of the ball, so it will displace the same amount of the volume of the liquid. So rho is the density of the liquid. Now viscous drag is 6 pi eta rv, that is also acting in the upward direction because it is opposing the motion. So this 6 pi eta rv, which is from our Stokes law, it is also acting in the upward direction. Now after some time, when it reaches to the terminal velocity, that time the velocity is no longer increasing, so we can say that the body is now moving under equilibrium. So we can say that the body has reached to the equilibrium state, so the net force is zero. That's why the ball is moving with constant velocity, okay, with constant velocity. So we can write the net upward force must be equal to net downward force. So here the downward force is mg, the upward force is upthrust, as well as the force that is given by the Stokes theorem or Stokes law, and that is equal to 6 pi eta r vt. In the subscript we have written vt, okay. The t indicates that it is the terminal velocity. So 6 pi eta r vt, this is v rho g, that is the volume of the liquid displaced, and this is v sigma g, the same volume is being used over here. sigma represents the density of the solid itself. So now we know that the volume of a sphere, okay, the volume of a sphere is 4 by 3 pi rq. So on putting all this value, we will find that the expression for the terminal velocity is this one, 2r square sigma minus rho multiplied by g divided by 9 eta. So this is the expression, and I think that if the question comes about the derivation of the terminal velocity, the question will be of 2 or 3 marks, okay, and the definition of the terminal velocity or the Stokes law, it will carry 1 marks, okay. Now there is a very special inference over here that we are getting over here, that is terminal velocity is proportional to r square, where r is the radius of the ball, okay. So remember over here that you must be wondering that which raindrop is moving with greater velocity, okay. Some drops are bigger, some drops are smaller. So here from this relation we can say that the larger raindrops fall with greater velocity. Similarly, you must have seen, okay, in the movie that or sometimes in the practical life, that the air bubble, okay, it rises up in the water. So here, if in the case I have assumed earlier that it is a metallic ball, just to get an idea about it, but it can be anything, okay. So if it is an air bubble, the sigma value, okay, the material which is constituting the air bubble, okay, that is the density of the air, it is always less than the density of the liquid. So in that case it will be negative, okay. So in that case the velocity will not be in the downward direction, it will be in the upward direction. This is why the air bubble rises up in the water, okay. So that's all, and just remember what are the effects that changes the viscosity. So we are finding that the increase in temperature decreases the viscosity of the liquid, and viscosity of the gases also increases, okay. So liquid decreases, but in case of gas the viscosity increases. Remember this thing. Thank you for watching this video, and I hope that it will be definitely beneficial for you, and requesting you to share with your fellow students so that he or she will also get benefited from it. Thank you.